Cool. Okay. So I want to continue our conversation about second order circuits. I'm not really sure how many lectures it's going to take for us to have this conversation, but I think it's kind of important. So we're just going to take as much time as it takes, and we're going to try to get it right. So somebody help refresh my memory. We had a voltage source going into, was it an inductor, a resistor, and then a capacitor? An inductor, a resistor, and a capacitor. All right, and let's see, 2 millihenries? Really, I guess, good memory. 2 millihenries, 2 kiloohms, and half a farad, microfarad, millifarad, microfarad. Okay, and we said this was the input voltage, and we said this was the output voltage, and we wrote ourselves a second order differential equation, did we not? Okay, and we said that second order differential equation was something like V out double prime plus V out prime over L over R or R over L? R over L. So R over L is in the denominator, not out front, right? If I stick it in the denominator, then it's L over R. Let's see, how do we want to do that? Okay, let's leave it R over L. Okay. Plus 1 over RC LC times V out equals, it was 1 over LC times V in, right? So we looked at that and we said, what? Okay, and it's important to know that differential equation didn't really depend on what my input signal is, right? At this point, I haven't yet cared that I'm putting in a step input or a sine wave or a whatever signal. So then we decided we needed to solve this problem. So we said, okay, let's just rewrite this as a generic second order differential equation and then learn how to solve that differential equation. So I decided to rewrite this as either one of 2 ways. The first way was how they do it in the book. It's y double prime plus a y prime plus b equals x. What's that? Oh, I'm sorry, I beg your pardon, by. The other way is to use the other method they talk about in the book, which is exactly the same differential equation, but to rename the variables a and b for reasons that I didn't really make clear yet, and it sort of seemed to make things worse, not better. Yes?
I got, on the right side, I got bx.
You got bx. Let's see if I can confirm or deny that. It sort of doesn't matter. Once you go to this mode, it's just a scale factor. So it's just we don't need to worry about that scale factor. But you can put the bx if you want. It's not going to change anything. Okay, so if we write it this way, do you remember it was y double prime plus, was it zeta omega naught? 2 zeta omega naught, thank you. Y prime plus omega naught squared y equals x. So it's the same thing, right? It's 3 differential equations, and I'm just calling the coefficients different stuff. Then we said we need to solve this differential equation. So we said, okay, anytime you solve a differential equation, you have to do the total answer is going to equal the particular solution plus the homogeneous solution. Good grief. Come on, Obaid. There we go. Particular plus homogeneous, same like we did with first order circuits. The particular solution is the solution that depends on the input. The homogeneous solution is the one that just sort of depends on the physics of the circuit. So in this case, we said, supposing supposing x of t is just a constant for, right, so if x of t is a step input, like see here how I've drawn a step input for my input. So if my voltage like starts at 0 and then steps up to some final value, like let's say it steps from 0 to 1, then what we decided that the particular solution in that case had to be that y of t was equal to that same constant a. So from a standpoint of, so this is what we did on, I'm recapping Monday still. So what we decided is that if my input is a step from 0 to 1, then my output is also going to go from 0, eventually it's going to get to 1, right? The long term, the steady state solution, what the differential equation tells us, if my input is a constant, my output will eventually be a constant. That's what the particular solution told us. Yes?
Why would they go to 1 and then disappear and then go back to 1?
Oh, this is, I tried to erase this. Good question. Right. And the dotted line is just there to just so you can see that it peels back to 1. Okay. So, eventually it's going to get to 1. So the homogeneous solution is going to tell us how it gets to 1. Right? And that's what we're going to talk about today. Homogeneous solution is going to tell me how you're going to get from here to here. Okay? With the first order circuit, we know what it did, right? With the first order circuit, we had something that looked like that, did we not? But maybe it's going to be different with second order circuit, right? It's like it's a whole different beast, right? Maybe it's going to go down and then up. Maybe it's going to wiggle. Maybe it's going to, I don't know, who knows, right? That's the whole point of this argument, is we have to talk about how you get from here to there. So, we had that conversation. So we solved the particular solution. Then we said, okay, now we need to know the homogeneous solution. And we did the guess and check approach. We guessed that the homogeneous solution was going to be an exponential. So that was our guess. And so what we did, we said, okay, if this guess is true, then that guess must hold true when we stuff it into the differential equation. So let's see if it works. Let's take that guess. Let's take its first derivative, its second derivative, mush it into the differential equation, and see whether or not the equation works. Like if the equation works, if it yields something that is true, then we know that that's a solution. And if it yields some sort of nonsense, like 0 equals 1 or something, or 0 equals 0 or something that just doesn't make any sense, then we'll know that that can't possibly be true. So we did that. We took this, we put it in the differential equation, and what we found was that this solution will work. Okay, so this is in fact the solution on the condition that S had to equal basically the solution to that quadratic equation. So if you take S squared plus AS plus B equals 0, this solution will work as long as the actual constant value for S that you choose. Like what's S? S is just a number, right? It could be -3, +4, 2.5. It could be a complex number. Who knows, right? So it turns out that this is the true answer as long as your values of S satisfy that equation. That's what we figured out on Monday. So okay, so you solve that equation. So you say, okay, S has to equal minus A plus or minus the square root of A squared minus 4B over 2. Is that not in fact the solution of that differential equation, or the solution of that quadratic equation? I don't know, is it? Tell me. I'm forgetful. I studied this stuff in the 80s. That's not a lie. I learned the quadratic equation in 1987.
Is for
Minus b, minus the middle term, plus or minus the square root of middle term squared minus 4 times that term, square root over 2, and then 1. I'm good to go.
is minus for AC.
This is A, and this is C. Yeah. A is B, and B is C. Yeah, sorry about that. I don't make this stuff up. Okay, or if we use this form for our differential equation, right? Because I could use this form or this form. It's the same thing, right? It's just numbers. If I use this form, if I use the form that says s squared plus 2 zeta omega omega naught. Is it omega naught or omega n? What did I tell you on Monday? Omega naught? Okay, and I'm still using that. Hooray. Okay. 2 zeta omega naught s plus omega naught squared equals 0. That's the same, it's the same thing. You solve for s. Now you get minus zeta omega naught plus or minus omega naught times the square root of zeta squared minus 1. Is that what we came up with?
Yes. Yeah. There was a 2 in front of the omega naught.
There was a 2 in front of this omega naught?
No.
That's it. I'm good. I'm good.
Oh, okay. No.
Don't mess with me. Don't say I screwed it up if I didn't. Okay. So, what it turns out is, mathematically, it doesn't matter. Like, you can solve it this way or this way. You're going to get the same values of s, right? It just turns out that if you think of the problem in this way, like zeta and omega naught have some sort of physical significance to the circuit, whereas A and B don't have any significance to the circuit. They're just kind of like numbers. But zeta and omega naught turn out to be pretty handy. So let's actually go ahead and solve using the numbers that we did. Oh, we even did that on Monday, didn't we? We did pretty good on Monday. We got you got your money's worth on Monday, right? Seriously, how much does it cost per lecture? Did anybody ever calculate that? Can't be that bad. What's a full semester's tuition? 7,000? 10,000? 8,000 in, okay, let's say 8,000 in, plus tax? Let's keep the math easy, right? Okay, how many courses are you taking? 4? Okay, how many lectures in each course? 30-ish? 32? Okay, so if I this should tell you the dollars per lecture, right? Okay, so let's see, 32, 64, 120, so that's the same as 128. So 8,000 over 128, that's 4,000 over 64, that's 2,000 over 32. How many? God, I can go 5 more times. 1,000, $65. Is that right? 63. Okay, so somebody did it for me. Thank you for putting me out of my misery. $63 an hour, right? I mean, let's get your. What's that? Yeah, for every class, right? Every class costs you $63. So I hope you get your $63 worth.
By 4 because 8,000 is the total tuition for the semester.
Yeah.
Oh wait, no, did you?
I did. Yeah. There was a 4 in there. Yeah, I'm on my game. All right. So in our particular case, let's go ahead and solve. Let's just go ahead and use this form in this case because I don't really need to figure out zeta and omega naught right now. I'm just trying to get values of s. So it looks like I'm going to have. Okay, so my differential equation is going to be y double prime plus, what do we say? We said r over L? Okay, so r over L is going to be, we said a million, 1e6, 1e6 y prime plus 1 over LC. Is that right? Seriously, I don't remember. So 1 over LC is 10 to the 9th plus 1e9 y equals 0. So that's the sorry, I should put s's here. That's the quadratic equation we're trying to solve. Is that right? Okay, and if we solve it, okay, I'm going to go to MATLAB, because MATLAB has a little equation solver in it for me. Roots of 1, 1e6, 1e9. Oh yeah, we did this. Minus 9.99 times 10 to the 5th. And I got another root, right? Quadratic equations always have two roots, right? Minus 0.01 times 10 to the 5th. Pretty slick, right? So, we're almost done.
Dr. Wing,
Yes?
did you get that first equation? That
Oh, this is, what I did was I started with my differential equation that said y double prime plus r over l y prime plus 1 over LC y equals x. That was my differential equation. So r over l, that's my a term, and 1 over LC, that's my b term. So r over l, the 2's cancel, you're left with 10 to the 3 over 10 to the minus 3 is 10 to the 6th. And then same sort of nonsense for 1 over LC. And whoever yelled out those numbers at me was very kind in giving us numbers that all canceled out very nicely, so we got coefficients that were not like 4 decimal places. Okay, yes?
If you give a problem like solving problem like this, how you solve? We don't have a MATLAB.
You have a calculator. Look, the equation's right here. That's how you solve it. You plug numbers into this equation. You have a calculator that takes the square root, I hope. So you'll need to know how to do that. Okay, I'm running out of precious board space. Okay, I think we're going to work here. So here's where we're at. So right now, in summary, we've determined that my total solution to this input step, y of t, has to equal the particular solution plus the homogeneous solution. We figured the particular solution, that was 1. That was this 1 right here, plus the homogeneous solution. And the homogeneous solution, we've determined, is always going to be in this form. Okay, so I've got K1 e to the minus 9.99 times 10 to the 5t. But I've also got another one of these, right? It turns out I didn't just get one of those k e to the st terms. I got 2 of them, right? Plus k2 e to the minus 0.01 times 10 to the 5t. Yipes.
So we took this, we just assume the value of 1.
What do you mean we?
It's not given.
This is y. I mean v out. I'm using v out and y interchangeably. Does that make sense?
Oh, so that thing is 1.
Yeah. This is v in is your input x, and v out is your output y. So I got tired of writing v out. And plus, when we write it in terms of y, then we're just thinking about the solution to a generic differential equation as opposed to something that's like always a circuit. Okay, am I done? I need K1 and K2. Okay? I need K1 and K2. And how am I going to get those? How do I always get these values? Initial conditions. So, let's assume that my input voltage was off for a really long time. So what do you think my initial output voltage is? What do you think V out should be at time t equals 0 if this input has been off? It should be 0. So I think I got an initial condition. My first initial condition tells me that my output voltage at time t equals 0 is going to be 0. So So let me come into my equation here and substitute in t equals 0, right? Because that's how that works, right? You just sub in t equals 0. So what does that give me if I sub in 0 into this equation? I get 1 plus k1, because e to the 0 is 1 times k1, plus k2. Okay, that's a cool equation. Am I ready? Am I done? Can I solve for k1 and k2? I need another equation. So what's my other initial condition? Any guesses? Any guesses?
I know.
Sort of. Right, you can assume that the current is... Okay, let's assume that you could assume the current is 0. If the current is 0, how would that help me? But this is a differential equation for voltage. So how can I turn current into voltage? So I definitely agree that the initial current is 0. But I don't have any current in this equation. So knowing that the current is 0 doesn't help me. But let's look at the relationship between the current and the capacitor. Right? What's the current equation for the capacitor? I equals C dV out dt. So if you're telling me that the initial current is 0, what you're really telling me is that the initial derivative of my output variable is 0. So really what you're telling me is that the first derivative of y at time t equals 0 is 0. Is that information useful to me? Totally. Right? Can I take the first derivative of this equation? Yes, I can. Let's try. Derivative of 1? 0. Okay, that's helpful. Derivative of this term? So that's going to equal 0 plus. Derivative of this term will be minus 9.99 times 10 to the 5th k1. Hold on. Now, I still have this e term, but what am I going to substitute in for t? Right? I'm still subbing in t equals 0. So when I sub in t equals 0, that term is gone. It just turns into 1. So I'm done with, so this is good. And now I move on to the derivative of this term. Minus 0.01 times 10 to the 5th times k2. And then I do have this e term, but then I substitute in t equals 0 into that exponential, and it turns into 1. Well, now we're getting somewhere. Now look at what I've got. I've got this equation, which came from the initial condition for y, and I've got this equation, which came from the initial condition of y prime, and it looks like what I've got is 2 equations and 2 unknowns. Can I solve? Totally. I don't feel like it, but I can. Okay. Well, how can we do this? What if we do a shortcut? Do you like shortcuts? Do you like to do the same problem over and over and over again? Right? That would kind of suck, right? Why don't we do this? Let me do a little aside over here before everybody gets all calculator happy. Let me assume that y of t was 1 plus k1 e to the s1t plus k2 e to the s2t. So basically exactly what we had before, but instead of sticking in numbers for s, I'm just going to leave them as s1 and s2. All right? Because it's always going to have this form, right? Your step response is always going to have that form. So I'm just kind of doing a general solution. So the first initial condition told me that 0 equaled 1 plus S1 plus, 1 plus K1 plus K2. That was my first That's what I got by setting my initial condition for y to 0. Okay? 0 equals 1 plus S1, K1 plus K2. My other solution for the first derivative told me that 0 equaled K1S1 plus K2S2. Is that right? I mean, I'm basically just writing the same equations. I'm just taking the numbers out. So why don't we just solve it once in terms of the variables? We'll get a nice little equation, and then we never have to solve it again. So again, our goal is to solve for K1 and K2. So let's see if I can do this by hand. If I start with this equation and solve it for, I don't know, should I solve it for K1 or K2? Doesn't matter, right? Let's solve it for K1. So according to this, K1 is going to equal negative K2S2 over S1. Is that right? Seriously, is that right? Okay. Now I'm going to take that, sub it back in here. If I do that, that's going to tell me that 0 equals 1 plus K1, which is minus K2S2 over S1, plus K2. So therefore, let's see if I can combine like terms. Negative 1 equals K2, 1 minus S2 over S1, which means negative 1 equals K2, S1 minus S2 over S1, which therefore means that K2 equals minus S1 over S1 minus S2. What do you think? And therefore, according to this equation, K1 is going to equal, so this says take K2 multiplied by negative S2 over S1. So that should give me positive S2 over S1 minus S2. So look what I've done for you. We've solved that stupid little 2x2 equation. And now instead of having to beat your head over and over again, solving it, working with all these awful numbers, just use the formula. Right? It's right there. Put it on your cheat sheet. Right? I'm going to give you an open note exam. Okay, so K1 is going to equal S2, which is this number. So minus 0.01 times 10 to the 5th divided by S1 minus S2. So minus 9.99 times 10 to the 5th minus negative 0.01 times 10 to the 5th. Oh, the 10 to the 5ths all cancel. That's nice. I don't know, what does that leave me with? Let's have a look. According to my calculator, and you should tell me what your calculator says, minus 0.01 divided by minus 9.99 minus negative 0.01. Somebody get the same number as me? I got 0.001. Is that what you got? Okay. So now, 0.001. Okay. And K2 is going to equal minus S1 over S1 minus S2. So that's going to be minus S1. So it's going to be 9.99 times 10 to the 5th over minus 9.99 plus 0.01. I'm guessing that equals, I have no idea what that equals. Yes. Which step to which step? This? This guy? Okay. I took the second equation, solved it for K1. Oh, they're two different equations. I didn't get from one to the other. This was the initial condition for y, and this is the initial condition for y prime. And then everything after that is just solving the equations. Okay, so what do we get for K2? I got minus 1.01. Anybody get that too? Minus 1.01 or 001? 001. Ta-da! Well, what does that mean? Yay, can we plot it? We could probably plot it. But let's talk about it. Okay, so I've got three terms. One of them is a constant. What's going to happen to those two exponentials as t goes to infinity? What's going to happen to this term as t goes to infinity? You're going to be left with e to the negative stuff times infinity. So e to the negative infinity, 0. So as t gets bigger and bigger, this term is going to go to 0. This term is going to go to 0. And you're just going to be left with 1. Does that make sense? Is that what we predicted? It is, right? We predicted that our solution, we didn't know what it was going to do in the beginning, but we knew eventually it would get to 1. So that's good, right? Go us. Now let's see what it does in the short term. So this is like a term with a time constant, right? And this is a term with a time constant. Which one has the bigger time constant, the first one or the second one? I'll give you a hint. It's a trick question. It's definitely not the same. Although that would be the correct guess for a trick question. Remember when we did the first order equations? It was always e to the minus t over tau. So what would be the time constant on this term? Let me erase some of this mess. Again, I don't just like writing equations and then just plotting the answer. I like to write equations and then think about what any of it means. Right? Because otherwise, really, what's the point? Right? Otherwise, you just make the computer solve the equation if we don't care to stop and look at it for a minute. So that's what we're going to do. Before we actually plot it, or God forbid, run a circuit simulator, we're going to talk about it, right? And see if we can build intuition on this stuff. This term is a constant. This term is like 0.001 e to the minus t over some time constant, where that time constant is... So what is 1 over 9.99 times 10 to the 5th? 9.99 E5. Ooh, it's small. 1.001 microseconds. So 1.001 microseconds. So you see what I did? All I did is I took that and I took its reciprocal. So instead of sticking it times t, I just stuck it divide by t. And I know if I do it like that, I can interpret that number as the time constant. And don't forget, we know what to do once we have time constants, right? We know time constants decay, right? And we know that they decay like 63% and then 86% and then 90 whatever it was and so on and so forth. Okay, let's look at this term. We have a minus 1.001 e to the minus t over so it's 1 over 0.01 times 10 to the 5th. So we get a millisecond. So which has the bigger time constant? Which one's faster? This guy, right? This guy, how long is it going to take for him to reach his 5 time constants and disappear altogether? Remember, your exponential decays, and it always, we said, after 5 time constants, it's basically decayed away. So how long is it going to take for this term to decay away? 5 microseconds. Blink of an eye. And this guy? By 5 milliseconds. So this is the one that's really going to dominate the equation. So let's look and see what happens. So we start over here at t equals 0. And initially, we know we're going to get 0. Because if I sub in 0 for everything, I'll get 1 plus 0.01 minus that. I'll get 0. So let's see. My first term is going to start acting very quickly. Like this term is going to be very, very slow relative to the second, relative to the 1 microsecond. So this term will start acting very quickly. And what's that going to do for me? Is it going to make my number go up or down? Maybe we should draw it like this. Maybe this is a cool way to approach this. I've got 3 terms, right? So let's start with time t equals 0. I've got term 1, which is my constant 1. I've got term 2, which is my 0.001 e to the minus t over 1, just call it 1 microsecond. I don't feel like writing all that out. And minus 1.001 e to the minus t over 1 millisecond. So right at t equals 0, this term donates a 1 because it's independent of t. This term donates, what do you get if you sub in t equals 0? 0.001. And this term donates minus 1.001. And if you add them all together, what do you get? 1 plus this number minus this number. 0. Hey, that was our initial condition, right? Of course it's going to work out that way. Okay, now let's wait for a microsecond. Okay? We're going to wait 1 microsecond. So this term donates 1. Thank you for being awake. All right. What's going to happen over here? I'll give you a hint. It's 1 time constant. So it's 63%. So if it was at 0.001, we know eventually it's going to get to 0. So it's going to be 63% of the way to 0. It's going to have lost 63% of its value. Meaning you're going to be left with about 37%. So I'm guessing this number will now be at 0.00037. If you don't believe me, just stick in 1 microsecond up here and see what number comes out. Or maybe I'll try that. Okay? So I'm going to take 0.001 times e to the minus 1 microsecond divided by 1 microsecond. Okay, I got pretty close. 0.000367. All right. So all I'm doing is I'm subbing in 1 microsecond in here. And I get that number. What about this term? What's this term going to donate? This is cool, right? It's kind of like slow and menial to go through these steps, but I think there's value in understanding how these equations are put together. Because otherwise, you don't really ever get an appreciation for it. Look, this has a time constant of 1 millisecond. Yet we've only gone 1 microsecond. So that's 1/1000th of 1 time constant. So has this thing really had a chance to decay yet? No, right? I mean, it's just like, it's like such a teensy-weensy little bit of time relative to this time constant. So I'm guessing that this number, if I were to take 1 microsecond and sub it in up here, which you're certainly welcome to do. I'm just trying to save you the trip to the calculator and build some intuition. If we were to sub in 1 microsecond into this equation, we would find out that we would still have basically something that was almost indistinguishable from e to the 0 and still be left with minus 1.001. Again, if you don't believe me, just go to your calculator, right? Minus 1.001 times e to the minus 1 microsecond divided by 1 millisecond. Oh, I forgot to put e to the minus. There we go. I get basically like, my calculator said 1.000. Let's not split hairs. Okay? But the point is that I want you to build intuitively. This term is decaying away fast. Okay? In 1 microsecond, it lost 63% of its value. Whereas this term, its time constant is huge. So 1 microsecond is like a drop in the ocean for him. So let's see what happened. If I add these three numbers together, this term basically stayed the same. This term basically stayed the same. This term got smaller. So what happened to the total sum? If it's same, smaller. It should get a little bit smaller. A lot smaller? No, but it got smaller, and I care that you know that it was smaller. Okay? So, very quickly, this guy is going to start to, the second term is going to start to drive it lower a little bit. Just for a teensy-weensy bit. Okay? How long will it take for this term to decay away altogether? 5 microseconds. So let's see what happens after 5 microseconds. This term is still 1. This term is now, he's still 0. And this term is, it's still probably pretty close to 1, right? So, in fact, we could actually get the exact value. I'm getting minus 9.996 times 10 to the minus, oh, I just put my decimal in the wrong place, minus 0.996. So this dipped down very quickly, but then almost immediately, this term starts to take over. Okay? So this term gave you a very, I'm exaggerating this dip, right? Remember, this dip all happened in less than 5 microseconds. Whereas, how long did it take for this thing to charge up all the way? That took about 5 milliseconds, right? This is about 5 microseconds. This is about 5 milliseconds. So it's totally not to scale. But I am very interested in the fact that there was a little dip there before. Because when we did the first order circuit, the Rlc circuit, there was never any dip. Now you've got like some new stuff that's happening, right? There's a dip there that wasn't there before. Okay? And so we have our final answer. And you know, we didn't even need to do all this. We could have just taken this and plotted it on our calculator and figured all this out, right? But I still think there's value in being able to look at this equation and peel it apart like an onion and figure out like what all the pieces do. Because if you understand how the pieces fit together, then you're getting somewhere. What do you think? I've got about 6 minutes of your time left. I'd like to do something. Can I pull this down? I want to simulate this and hopefully try to make some useful points in the process. Has everybody used Multisim? Multisim is just like, it's a piece of work. It's a very powerful piece of software, but you know, it's not always the most pleasant thing to use. And I was poking around online, and I don't know if you've seen this tool, but I'm going to show you a tool that I've discovered. Show me, hold on. So here's my problem with Multisim. I use one of these. Doesn't speak multisim. So we search for source on VGA2. There we go. That was a good sound. Hey! So I poked, and I discovered this website, www.circuitlab.com. I went and I created myself a free account, and here's what I discovered I can do. I'm going to click on my workbench. I'm going to create a new circuit. Alrighty. So let's see what we can do here. Let's put in a voltage source, an inductor, a resistor, a little easier than multisim, eh? Capacitor, and it's so pretty. Okay, I'm going to wire it together. Oops. Okay, let's change these values. So this needs to be 2 millihenries.
Is it free or?
It's free 99. A language I understand. And let's see, we said a half of a microfarad, and I'm done. 500 nano is the same as half a micro. I actually went and typed in, look at that, I typed in 0.5 U. That's half a microfarad. That's the same as 500 nanofarads. Whatever. Okay. Oh, it needs to know where ground is, so there's ground. I do want to name this node so I can refer to it. We'll call that V out, and I'm done. Now, here's one cool thing you can do right off the bat. Oh, I got to save it first of all. Save Rlc Circuit. So here's one thing I can do. Suppose you need to make a graphic, like for a paper or a report or something. You can say, please export this as a PNG. And it'll create a graphic for you. Cut and paste. All right? It's very nice. But I'm actually interested in simulating it. So I'm going to, there's a button down here that says simulate. I can do a DC DC run, a DC sweep. I actually want to do a time domain sweep. So let's see. How many seconds do I want to run it for? You know the time constant of this circuit. Do I need to wait a whole second to see this thing do its business? No, I think I can wait maybe like 5 milliseconds should be enough. Let's make it 7 to make it interesting. So 7 milliseconds. Time step, let's do a nanosecond. And, oh, what do I want to output? I'm just going to click right here. I'd like to output V out. I think I'm good. Let's run that. Error in transient solver. Boo. Okay, let's try 10 nanoseconds. Oh! Solver, illegal start or step. Well, it didn't do this at home last night. Oh, come on, Obaid. Oh, yes. Thank you. I would never figure that out. Okay. It's going to take a while because I asked it to do a whole lot of points. Okay, that's actually way longer than I'm willing to wait. Can I get back in here? Solve aborted. Now plotting partial results. And of course, because I'm using this, hold on. How do I get out of here? Okay, I might have that kind of patience. Not really, though. Okay, yes?
How did you, I didn't see, how did you get voltage out that level?
There was a button called Node Name, and I just clicked on the Node Name button. I clicked on the corner, and I gave it a name. Okay, now, while it's running, I want you to look here. there's a button that says sweep parameter. Here's what we're going to do on Friday. When you click the sweep parameter button, what it's going to do is to give you the option of running the same simulation a whole bunch of times. Like right now, it's just running the simulation once. But I can say, run this simulation 5 times for 5 different values of, say, R1. Isn't that cool? Because I think what you're going to find is going to happen is I change my values, like all this 5 microsecond, 5 millisecond time constant, all that baloney, that was dependent on these specific values of R and C, RL and C. So my question now becomes, cool, what happens if we change R? Do we need to resolve this thing from scratch? And, you know, I don't really feel like doing it. I'd like to simulate it, but I would like to have some intuition behind it. Now plotting. I think my underpowered MacBook Air is going to catch fire. Well, we may have to pick this up on Friday. It's done. That's a good sign. But anyway, software tools. You can do all this in multisim as well. I just like this because I can run it on my Mac without having to install VMware. But basically what we'll be doing is we'll be varying the value of this resistor and seeing what happens. Yes?
Is that only online, or do they have like a download?
I think it's only online. I haven't looked to see if they have an offline version. That would be nice.
Not a favorite website.